So here, let me, good catch. So let me remind you about the cylindrical Bessel functions. They're given by this sum, and as we saw for small z, they look like this. They just go as z to the n. For large z, they go as a cosine. And this n pi is a sort of eigenvalue in some cases. They satisfy this last differential equation. This is Bessel's equation. And these are the first, I guess, 5 Bessel functions. And you see that they're all 0 at 0 except for J0, which is 1 when rho equals 0. And there are these various identities that we went through last time. Let me also say that if you take that original formula for the cylindrical Bessel function of the first kind, actually, and you replace n, an integer, by nu, an arbitrary, actually I guess you could make it an arbitrary complex number. It doesn't even have to be a real number. Since nu only occurs here and there, here it occurs as m plus nu factorial, so you rewrite that as gamma of m plus nu. So if nu is any real number or any complex number, as long as you don't get the argument of this to hit a negative integer or 0, this is well defined, and this gives you, this extends Jn of z to non-integral values of n. Anyway, as I was saying last time, if you want to think about the Bessel functions as a self-adjoint system, then and then you pick an interval, and if the interval goes from 0 to b, then you want the Bessel function to vanish when x is equal to b. So you multiply. You have, instead of Jn of x, you have Jn of x over b times Znm. That's the nth 0 of the nth Bessel function. And you saw the Bessel functions go like this, so they keep crossing the x-axis, and they have an infinite number of zeros. Moreover, the eigenvalues then are basically z squared over b squared, and they are roughly m pi squared over b squared. They increase without limit as m goes to infinity, so the Bessel functions are complete and can represent differentiable functions on the interval that are normalizable and I guess that vanish at the two endpoints. They then form an orthonormal set, well, normalized in this way. They're orthogonal. For different values of m, you get this orthogonality relation. And the curious thing is that the normalization factor here is the square of a derivative of the Bessel function. And so then when you rewrite you go back to the original formula for the Bessel function in terms of the eigenfunctions of a self-adjoint system, you then write it this way, and for n equals 1 and b equal to 1, there's the sum is like that, and as I said, I think I may have used both methods. Anyway, I computed this for J1. In an earlier chapter, I did a similar series for based on J0. So we stopped last time talking about Bessel's drum. It's not really Bessel's drum, but you can apply Bessel functions to the drum, and I imagine that he did. And so, first of all, if you have a if you have something like this, then a small element, the length of that small element will be the square root of dx squared plus dy squared, and so that will be square root of dx squared plus, if this is the height, or actually it would be dy dx squared, dx squared, and so altogether it's square root of 1 plus dy dx squared times dx. But here the y is the height above the drum, above the surface of the drum, or the displacement of the surface of the drum. So you get h sub x, the x derivative of the height squared. And then if you also look at it, an interval perpendicular on the surface of the drum, you then, and you call x and y the angles. Here's the surface of the drum, and you're talking about x and y like that, then you have this formula here for the length of the small element of surface length in the y direction. And so the extra area is those two multiplied together minus 1 times dx dy. And so approximately for small displacements of the drum, you get this expression. And you take the surface tension, S sigma to be the surface tension, mu the surface mass density, then the kinetic energy of motion is mu ht squared times dx dy, and this gives you then the action of the surface of the drum. So you then, of course, vary the action to find out how the drum actually vibrates, and in the usual way you get this expression where this is the small change in the height of the height at x, y, and that then gives you this differential equation, which is a wave equation in 2 dimensions of space and 1 of time. It's separable. You set h equal to s of t, v of u, v of x and y, and you get this expression. In other words, you just write HTT here gives you STT times V, and then over here you get VXX times S. So if you divide by SV, you get this expression. And this is a function only of T, this is a function only of X and Y. So both of them have to be constants, because you can't have a non-trivial function of T equal to a non-trivial function of X and Y. And so you call that minus omega squared. And then the eigenvalues of this Helmholtz equation give you the angular frequencies. And you then write the time dependence like that. Then, of course, as we saw previously in polar coordinates, Helmholtz's equation is separable, and now I'm switching from x, y on the surface of the drum to theta and phi, so we're talking about the drum like this, theta and a distance r. And we just write v as u of r, h of theta, and then this thing separates, and you get this expression dividing by UH. You then get a function of R is equal to a function of theta, and that they both have to be a constant n squared. And so the solution for H is very simple. The solution for U is something that has to satisfy Bessel's equation, and when one writes it then in this form, where RD is the radius of the drum, and those are the eigenvalues. And so the total solution is this rather complicated expression, an infinite series on n, and then for each n, which gives you a Jn here, you have an infinite number of m's, where these are all the zeros of the Bessel function. Then you have your sine, your two sines. And you might say, well, why don't I have cosines? Well, I have a hidden cosines because I have t minus t0 and theta minus theta 0. And for big N and for each n and big M, the 0 is near this value, it turns out. So let's go down a little bit here. So that's the end of the example. The rest of this is that Helmholtz's equation separates in cylindrical coordinates in 3 dimensions, and that's where it's often used. You then have B of rho, phi of phi, and z of z, and so that's the equation. And there are 2 classes of solutions. One is when B rho obeys Bessel's equation, while phi and z satisfy these equations. The other possibility is B rho obeys the same equation but with a minus sign here, and phi is the same, but now z behaves differently. So this z is one that is exponentially decreasing or increasing. In this case, here it's an oscillatory function, e to the I k z. And what we have then is, in the first case, where the z's are real exponentials, you have this expression where these guys are going to go to 0 or to infinity. And on the other hand, if you use the oscillatory z functions, then Jn has this form, and these guys are just the phase factors. N must be an integer if the solution is if all values of phi from 0 to 2 pi are physical. Notice k is bounded here because when k gets greater than alpha, you have an imaginary, you have a negative, square root of a negative number, so this is imaginary. That doesn't mean you're out of luck, it just means that you're dealing with a different, with a modified Bessel function. And we'll get to them in just a second. The discussion on the previous slide simplifies when alpha is 0, and in that case the k term goes away, and so you just have Jn of k rho, or Jn of I k rho. So that's k equal to 0, you just have square root of minus alpha squared, and so, I'm sorry, it's alpha is 0. So you have Jn of k rho in the real case, and Jn of I k rho in the imaginary case. And this function here, multiplied by I to the minus nu, is known as a modified Bessel function. And it occurs in solutions of the diffusion equation, for example. And one can one can write the general diffusion equation after replacing this by, I guess, alpha squared V. One then it solves this equation, and the solutions are, in the one case, if Bessel, if B satisfies this Bessel equation and phi and Z satisfy that one. Here, let me. Or alternatively, you have this situation where phi and Z are like this. So these are the oscillatory ones in Z, these are the real exponentials in Z. But now, let me just move this up so that we see what the answers are here. So in the first case, with real exponentials, you have a modified Bessel function like that, whereas in the second case, you again have a modified Bessel function, but it's of alpha squared minus k squared. And of course here, if k squared is greater than alpha squared, you get this imaginary thing, but you already have an imaginary argument, so you can pop back to an ordinary Bessel function. Okay, so those are the cylindrical Bessel functions of the first kind, and they're modified versions. I think we can skip the biophysical example, but I'm going to hold class tomorrow in case anybody comes, this being Thanksgiving week. But if you want, I'll go through the biophysics example in detail. I think maybe I should go through the cylindrical waveguides, unless in your electrodynamics classes you've had waveguides so many times that you're just bored to tears. On the other hand, if you haven't yet had your heavy-duty, bone-crushing electrodynamics course, then maybe I should go through the cylindrical. Yes? Okay. All right, cylindrical waveguides. This is actually quite interesting, and it provides a very nice example of Bessel functions. More interesting, I guess, than Bessel's drum. What you've got is an electromagnetic wave in the z direction. Well, it's going to obviously have this phi dependence, e to the I n phi, and it's going to go in the z direction as a plane wave. And E will be some function then of rho, and B will also be a function of rho. And, well, I shouldn't say just rho, but anyway, E we can write as the rho component, the phi component in the phi direction, the z component, the z direction, and so much for B. If the waveguide is evacuated and perfectly conducting, if the waveguide is a perfectly conducting cylinder that's evacuated, then on the surface the components of the parallel components of E and the normal components of B vanish at the surface. So you have E in the z direction vanishes, and E phi at R vanishes, and the rho component of B vanishes. And if you now write the equations, the Maxwell equations, curl E equals minus B dot, and curl of B is E dot over C squared, then you can see that those 6 equations, if E and B are given by that, and if the phi and Z component, the phi and Z, and I'm sorry, the phi and T and Z dependence goes like this, then what we have is this, these equations, and actually I haven't yet used the phi and Z dependence, how it depends on phi and z, in that case, you get these expressions that E rho, you can solve for E rho and E phi, B rho, and B phi, and this is the rho derivative of the z component and the rho derivative of the z component of B, and so forth. The fields EZ and BZ obey these wave equations, and since their z dependence is periodic, they're linear combinations of this Bessel function. So these are the solutions that I just went through on a previous couple of slides, namely that I think this was alpha squared and this was k squared, although I may have had alpha and k playing opposite roles. You now can have, if you have B, the z component of B vanishing, then B is only transverse to the direction of propagation, and those are called transverse magnetic modes, or TM modes. And the boundary conditions for them are satisfied if this expression is a zero, ZNM of Jn. Remember, the normal component of B has to vanish when rho is equal to R. And so that gives you an equation for the frequency of the NM-TM mode. And it's then given by that, where K is the wave number in the Z direction. And so the first zero of J0 is J01, which is about 2.4. So the minimum frequency, J01, is given by this expression, C Z01 divided by R. You just set K equals 0 to get the minimum possible frequency. And if the radius of the waveguide is 1 centimeter, then this is about 11 gigahertz. So I guess that's the lowest frequency you can have in a waveguide with a radius of 1 centimeter. I guess that would be the conclusion. Using all these frequencies, a pulse moving in the z direction then is a sum on n and m, and you have these expressions for the zt dependence, this for the phi dependence, and the non-trivial thing is Jn of ZNM rho over R. So these are all the TM modes. Now if E is transverse, which is to say EZ vanishes, these are called the TE modes, or the transverse electric modes. And these boundary conditions are satisfied when, once again, omega squared c squared minus k squared is a 0, but now a 0 z prime nm of j prime n. And I must say, just at the moment, I forget why it's a 0 of j prime. That's presumably clear from the previous expression. Well, I'm not quite sure why, unless it's that this is the rho derivative of BZ, and that may be where the prime comes from. In any event, the first 0 of J11 is at 1.8, and so the minimum frequency is this, and that's about 8.8 gigahertz. So the TE mode apparently can have a lower frequency. than the TM mode. Do you want to hear about a cylindrical cavity, or should we skip that?
So I had a question.
You have a question, yeah?
Regarding the, so this is with a cylindrical or with a circular waveguide. How does it differ with a rectangular waveguide?
Oh! A rectangular waveguide is probably a lot simpler to analyze, because then what you've got is you just, I guess, have sines and cosines in the transverse directions, and then the ZT dependence would be the same. But yeah, it would be, you know, a lot simpler mathematically.
So is the difference between the TE and TM modes, is that why most waveguides are rectangular and not square?
Well, I don't know. I don't know what the difference. You're saying most waveguides are rectangular?
The ones that I've seen that we usually use are rectangular in profile.
These are physical,
Physical.
not mathematical in class.
Right.
I don't know.
I know they're
when I see coaxial cable, that's a waveguide, isn't it?
Yeah.
Those are round.
But
That's circular.
But waveguides for electromagnetic fields are often rectangular.
All right. I do not know why the ones that you're talking about are rectangular. They're certainly easier to analyze mathematically. I would think that physically they have very similar properties, but I don't know. I haven't analyzed them. You know, I was just concentrating on Bessel functions, so I did the painful cylindrical case here. If I ever am silly enough to do a third edition of this book, I think I will do earlier in Chapter 7, the chapter on differential equations. Rectangular waveguides would be a nice example. So thanks for bringing it up, but it just didn't occur to me. Okay, let me do a topic that I should have emphasized more in the book, and so I mean, I did have this graph in the book, but I think there's a little bit more to say. These are the Bessel functions of the second kind, cylindrical Bessel functions of the second kind, and let me show you how they're defined. They're called Y nu, and one writes them this way: cosine of pi nu, J nu of Z minus J of minus nu of Z, and you divide the whole thing by sine of pi nu. Now remember, J sub minus n is essentially a phase factor times J sub n. And that means that this thing is singular when nu goes to n. And in fact becomes 0 over 0, because this is 1. This thing with J sub minus n is, actually it's not n, it's not 1, it's minus 1 to the n plus 1, I think, because cosine of 0 is 1. So it's minus 1 to, yeah, minus 1 to the n, and then this one is minus 1 to the n j n, and so you get 0 here, and on the other hand you always get 0 when n is an integer here. And so you have to use L'Hopital's rule to take the limit. You differentiate the numerator and denominator, and then set nu equal to n, or minus n, and that gives you this combination of expressions. But anyway, this is the general form for the simpler expression for non-integer values of nu. It's this ratio, but when nu is an integer n, then you have to use this expression, and these are the nth derivatives of J nu. So these are called Bessel functions of the second kind, And as you see, they all diverge at z equal to 0, and that's true whether or not, whether nu is an integer, as in these examples, or a non-integer, and that's because of the j minus nu. The j minus nu has a 1 over z to the nu, essentially, in front of it. So these are those expressions. These are the expressions. So now we come to the nice Bessel functions. The nice Bessel functions are the spherical Bessel functions. And when you see the definition, you'd say the first thing that would occur to you is, gosh, this is even worse because it's j of L plus a half, and j sub L is bad enough. J of L plus a half must be worse, and then we're dividing by square root of x. So this is really terrible. But in fact, it's just miraculously simple. It's that j of L plus a half is square root of x times the spherical Bessel function. Spherical Bessel function satisfies this differential equation. The spherical, the equation for a spherical Bessel function, and as we'll see in a moment, these are very simple functions compared to the cylindrical Bessel functions. So we saw earlier that if you're taking Helmholtz's equation and you go to spherical coordinates, the thing separates, and so you can rewrite Laplacian of v over v gives you then this expression. It has to be minus times r squared is minus k squared r squared, and that gives you a term involving r, a term involving theta, a term involving phi. So you set phi equal to e to the im phi. You set capital theta equal to the associated Legendre function, and then what you're left with is you set RKL of R equal to JL of KR. R has to satisfy this equation, and if you make this substitution, you can see that you actually have a solution because of because JL satisfies the spherical Bessel equation. Lord Rayleigh, whose actual, I always thought his name was actually Rayleigh or Raleigh, or however the hell one pronounces that name. I've never known how to pronounce it. His name was actually John Strutt, but because of his distinguished mathematics, he was made a lord. Anyway, he derived these formulas for the spherical Bessel functions, and you can see you just take sine x over x and you just differentiate it, and L times, and that gives you the spherical Bessel function. And so J0 is sine x over x, J1 is sine x over x squared minus cosine x over x, and you then get a recursion relation like this. Let me, while I'm at it, get a fresher piece of chalk. So if you look at the series expression for Jn, which we looked at in the beginning of the class, you can see for small rho, the spherical Bessel function goes as rho to the L. And for large rho, you can use Rayleigh's formula to compute it. And if we just look at J1 to start with, it's d by d rho of sine rho over rho. And so you see what happens is that when the rho derivative hits sine, it just changes sine into cosine or cosine into sine. But when it hits the 1 over rho, it brings down an extra factor of rho. And so this is much smaller at large rho. So the approximate value of JL of rho at large rho is just given by Rayleigh's formula, in which you let all the derivatives act on the sine. And it turns out that you can figure out what that is, namely it's either a sine or a cosine, and it turns out to be given by this formula here. And the error falls off as 1 over r squared. So this is a pretty good approximation. And in fact, somewhere I have a figure 9.4 that shows that. So here are the approximations to the sine rho minus pi over 2 over rho, and that's for J1, and for J2, I guess I have just sine of rho minus pi over rho, and so you can see that for large rho, you get a pretty good approximation. The dashed ones are the approximations for small rho, and they're doing pretty well as well, essentially rho to the L. So let's see, I skipped ahead a bit there. So I think we're done with that. These spherical Bessel functions satisfy a self-adjoint Sturm-Liouville equation like this. This is just the spherical Bessel equation. And the eigenvalue is k squared. The weight function is r squared. And the zeros of the spherical Bessel function are ZLN. That's the nth zero of the Lth spherical Bessel function. I probably should have used M instead of N. And they're orthonormal functions normalized by this expression on the right-hand side. And notice what we're doing here, the weight function is r squared, and of course that's the volume, that's what you have when you do the volume element in spherical coordinates, r squared dr sine theta d theta d phi. So this is the r squared dr part, and so that's the orthonormality relation. The system is specified by L, and the eigenvalue is specified by N. And these eigenvalues go as n plus L over 2 squared. And so they go to infinity, which means the JLs are complete. And in fact, here's a formula for the delta function. So one can then expand an arbitrary function of R as R to the alpha AN JL of these eigenfunctions. And you use the orthonormality equation to get the coefficients. And so all that's for a finite interval. Now I'm just going to quote the results for infinite intervals. For infinite intervals, you can have two relations which are just related to each other by just a change of variables. Delta of k minus k prime, thinking of those as the eigenvalues, are an integral r squared dr, JL of KR, JL of K prime R, and then you replace K by R, and you get delta of R minus R prime is JL of KR, JL of KR prime, K squared dk. Now this stuff is just a Schwingerism. Schwinger was remarkably good at mathematical manipulations, and in fact there was a rumor that back in the, I guess, 1950s, Schwinger would wander around the physics department at night, and when he passed desks that graduate students had, but the graduate students had gone home to go to sleep, and Schwinger would just walk them through, he would look down and see some problem that the graduate student was working, and the graduate student had stopped in the middle because he got stuck, and Schwinger would write the rest of the solution down, and he apparently did this many times and solved the problems of many graduate students while they were sleeping. That's a rumor. I don't know if it's true, but it strikes me as very possibly true. He was a very nice man. As I said, he was a Nobel laureate. In fact, the time I was taking quantum mechanics from him the day that his Nobel Prize was announced. And so that was kind of nice. Anyway, here's a typical Schwingerism. I don't know if, do you want to go through this in detail? What do you think? It's, all right. All right, let me just go through it quickly then. This is just 1 over z d by dz of that. Well, that's pretty clear what happens. And then here's the trick here. X dx is the derivative of this, or the differential of this. And then you can integrate by parts because x squared minus 1 vanishes at the endpoints of this interval. And so you're back to, then you have the differential of e to the I zx, and that cancels the z and the I, the minus i's, you get this. So the net thing is this is equal to that, and you can then do it L times and you get this expression. Now on the right hand side, that should sort of remind you of Rodriguez's expression for the Legendre polynomials. And in fact, if you use this integral, the J0, which is sine z over z, is equal to this, and you use Rayleigh's formula for JL, which is a derivative of JZ, of sine z over z, then you replace sine z over z by this integral. Then you use these expressions to take d by dz on this to be this, and then you generate the z to the L by differentiating the exponential, and now you integrate by parts and drop all the surface terms, and what you wind up with is an expression for the ELF spherical Bessel function as an integral involving Rodriguez's formula, which gives you the Legendre polynomial. So this is a remarkable result. It tells you that the spherical Bessel function is the Fourier transform of the Legendre polynomial. Who would have thought? This turns out to be very useful in physics because, well, let me just show you. It has applications in scattering theory. In particular, if you replace z by kr and x by cosine theta, then that gives you the formula I to the L JL of kr is given by this expression. So the Fourier transform has changed. When I said Fourier transform, it was actually not quite a Fourier transform because we weren't integrating over a full, the whole real line. So you can then rewrite the Fourier-Legendre expansion for e to the I kr cosine theta, and maybe I should write what that is. Let me see if I can find it easily. It's 931. This is something we learned in the previous class, so well, last week, I guess. So this is this expression. F of x can be written as a sum 2n plus 1 over 2 Pn of x integral minus 1 to 1 Pn of x prime f of x prime dx prime. And so you see that this sum of outer products of Legendre polynomials, of course, is a delta function. Anyway, this is called a Fourier-Legendre expansion. It's not obvious why the name Fourier is attached, but anyway, one does so attach it. And so, in other words, what you do here is the Fourier-Legendre expansion for e to the I kr cosine theta, which is e to the I k dot x really, is this expression. So this is just what I wrote on the blackboard for f equal to essentially e to the I k dot x. And on the other hand, this expression here just gives you a spherical Bessel function. So this gives you the equation, this is the derivation of the equation of e to the I k dot x is a sum of PL of cosine theta spherical Bessel functions. That's something that's used in scattering theory a great deal in non-relativistic physics. It's probably used in electrodynamics as well. If you go to polar coordinates and then what you have is e to the I k dot r, this expression becomes 4 pi I to the L JL of kr, and then spherical harmonics YLM, Y star LM of the other angle. So this is using the addition theorem to replace cosine PL, the Legendre polynomial of cosine theta. And so, as I was saying, this is this example. This is important in quantum mechanics. So let's see. Have you guys had the graduate quantum class yet? Okay, but you'll have it next year or something. All right. So let me go through this example because it will help you when you take a graduate quantum class. So we've just seen that the wave function for a free particle is e to the I k dot x minus I omega t, or IET, and the spherical Bessel functions are the part of the plane wave that the components of the plane wave that have definite angular momentum. So the Hamiltonian for a free particle, of course, is p squared over 2m, and the eigenstates, well, there are all kinds of eigenstates of the free Hamiltonian, but the ones that are not only eigenstates of the free Hamiltonian, but also eigenstates of angular momentum are called the KLM states. And H0 on it is p squared over 2m, or h bar k squared over 2m. L squared on them are h bar squared LL plus 1, and LZ is h bar m times that. And the inner product of R with a KLM is KJL of KR times the spherical harmonic. And the inner product of the two different KLM states, well, you just take this wave function and integrate it with respect to the complex, multiply by the complex conjugate of the other, and you get this expression here that you integrate. Well, this is there's an orthonormality relation here, and so that gives you delta LL prime, delta MM prime, because the spherical harmonics are orthonormal. And then these JLs are also orthonormal. I wrote that down on a previous slide. So this inner product is delta of momentum and then deltas of angular momentum. And the quantum mechanical completeness relation is that the unit operator is then a sum of outer products of these, of the ket and bra of KLM, summed over all L and all M, and integrated over K. And the inner products with an eigenstate of momentum is then this expression here, and so that's a YLM star, and it's since both are sharp in momentum, we have a delta function of momentum. And so now if you use the expression for this expression here, and the earlier formulas, in particular this one, you can write e to the I k prime dot r, which is the inner product of the bra r with the ket k prime. You write it this way, and that means that you have to sum over L and M and integrate over K. And this one here gives you the JL of KR, this YLM. This one gives you a YLM star. So what you get is JL of KR and then YLM, YLM star summed over all L. And so let me just go back to this one. This is an expression that is used in non-relativistic quantum mechanics to describe scattering. And as I said, it's probably used in electrodynamics and optics as well. And here we've integrated over K, you see. And, well, anyway, I skipped the derivation of that. If we go to the small KR approximation, then the probability that a particle with angular momentum h bar L is close to the origin, in other words, has R less than 1 over K, that would be an integral. The angular part just gives you essentially unity, or 2k squared over pi. You integrate from 0 to R, JL of KR prime, R prime, DR prime. And that gives you approximately, well, the approximation for small l is R to the L, so you have R to the 2L plus 2. There's the 2. And, oh, those should be primes on these R's. And you then get this expression here. So what does this say? This is very small when K is small and L is big, because then KR is quite small. If L is big, you you've got a small number to a high power, and that gives you essentially Zippo. You've got to go at this time. And oh, he's not teaching today? Or, don't you have your other class now?
That's on Wednesday.
Oh, you're right. Yeah, sorry. Okay, so this is something that's used a lot in physics, namely that a particle with an angular momentum that's angular momentum L, the probability that it's at small r is quite small, unless it's traveling unless it has high momentum. And in fact, that's how people first realized that nuclear forces were very short range, because they found that when they scattered pions or nuclei or protons or neutrons off nuclei, what they found was that that scattering was typically S-wave, that is to say L equals 0. And, well, what does that mean? That means that there wasn't any scattering of the higher L states, and so that the interpretation then was that the force was of such short range that it could only affect the particles that got really, really close together, and those were the S-wave states. And close here is 1 Fermi, or 10 to the minus 15 meters. That's typically the length of the strong interaction force. You might assume, if you're new to physics, that we understand all of this. No. Why nuclear forces are short range, why the quarks, because the neutrons and protons are triplets of quarks, and then pairs of quarks and antiquarks, and gazillion gluons. And the gluons are massless particles. Why don't we see the massless gluons? Why are the quarks confined? Why is the force of short range? None of this is understood, really. There are path integral calculations done on computers with by replacing space-time with a four-dimensional lattice, making various other approximations, and these support the conclusions, but I would say the understanding is essentially Zippo. And it's one of the embarrassing features of modern physics. On the other hand, we can look back 100 years and we know how little the guys knew 100 years ago or 200 years ago. So if you say that, you don't feel so bad. Anyway, if a potential is of short range, then at big R, the scattered wave function will look like this, and it'll differ. Well, what we're doing here is we're using Rayleigh's approximation. We're using the approximation for the spherical Bessel one here for large R, and it's of this form: sine kr minus L pi over 2 over kr. So you get this expression. That then you can rewrite in this way, and you can then show that the total cross-section of scattering is 4 pi over k squared times this sum, where the delta L's are called phase shifts. The next topic here is quantum dots, and here the idea is that an example of a quantum dot is a cadmium-selenium sphere, radius less than 2 nanometers, And photons excite electron-hole pairs, which then fluoresce in nanoseconds. If we model a quantum dot as just an electron trapped in a sphere of radius A, then the wave function will satisfy this equation with a boundary condition that the wave function is 0 at A, and one takes the potential V to be constant and negative for R less than A, and infinite and positive for R greater than A. And K squared then is 2ME minus V over H bar squared. We set that equal to, you remember in the Bessel's equation, we had that K squared was the 0 of the Bessel function squared divided by the length of the interval squared. And here the interval is 0 to A. And so the unnormalized eigenfunctions are a spherical Bessel function, a spherical harmonic, and then a theta function, which is 1 until we get to R equal to A, and then right, it's 1 until R is equal to A, because if R is bigger than A, then theta, you have theta of a negative number, which is 0. These zeros fix the energy levels as H bar times the 0 divided by A squared over 2M plus V. For the 0th Bessel function, they're essentially they're n pi, and so we have H bar n pi over A squared over 2M plus V. The coupling to a photon is like P dot A, and so one expects delta L equal to 1, and the energy gap from the NL equal to 1 state to the N equals 1, L equals 0 ground state is then the difference of these two energy eigenvalues, and so that's Z squared minus pi squared times this expression. And so it turns out H bar C is 197 EV nanometers, MC squared is half an MeV. The 0 Z12 is about 8, and so delta E2 is about 2 EV, and that's red light. So you expect red light from a quantum dot with radius 1 nanometer. The next 0 gives delta E3 to 4.14. That's in the visible range of A is in this range. And, well, there's just a remark about the Mathematica. Bessel functions of the third kind. Well, we were talking about Bessel functions of the third kind back when we did integral transforms. And we showed we could write the Hankel functions in this way. When Z is rho and lambda is nu are both real, they're complex conjugates of each other. And if you look at their real and imaginary parts, the real part is the cylindrical Bessel function of the first kind. The imaginary part is the cylindrical Bessel function of the second kind. Also called Neumann functions, and they're also called Weber functions. If you let Z be imaginary, then we get modified Bessel functions. For example, I alpha or K alpha, and a few simple cases are these. And of course, when do you need these Bessel functions that diverge at the origin? Well, you need them if you're dealing with a physical problem in which the origin doesn't appear. And an example is a coaxial waveguide, where what you've got is something that looks like this. So this is metal, and that's metal also. So this is So the electromagnetic fields are in this region here, and they don't penetrate smaller than this radius here, and they don't get any farther from the origin than this radius here. So they're in this region between this point and that point. So in that case, you see, this rho equals 0 is not part of the physical region. So you need both. You need the Bessel functions of the first and second kind. And so you write Ez as Jn plus Yn for E of rho and phi, the Z component, let us say. And one then gets these boundary conditions, and then the boundary conditions in turn can be satisfied if you have this expression vanishing, and here V is R over R0, X is given by that. And in GitHub I put or GitHub, I don't know how to pronounce that. Anyway, I put the MATLAB code to solve some of these things. Let's see, we have 4 minutes left. Spherical Bessel functions of the second kind. Well, these are given by a formula that's similar to the formula for the spherical Bessel functions of the first kind. You just change J to Y. And the Rayleigh formulas give them this very nice expressions. You see that they're diverging at rho equal to 0. For large rho, you let the derivative in Rayleigh's formula act on the cosine, and then you just get 1 over R times the L through to the cosine, and that's just a cosine of phase shifted. And at small rho, they go as rho to the 1 over rho to the L plus 1, and they're all infinite at 0. They're used for scattering off a hard sphere because, once again, the R equals 0 is outside. If the sphere is hard, then the wave function never penetrates to R equals 0. And so your L wave function, which is an angular momentum eigenstate, has to be a linear combination of both spherical Bessel functions. And the boundary condition that the sphere be hard, which is that the wave function vanishes at the surface of the sphere, that gives you the ratio of D to L, and you can then compute the phase shift. I think I'll just sort of skip the rest of that. Let's just look at the spherical Bessel functions. Once again, they're nice functions, and you can approximate them as cosines for large, cosine over rho for large rho, and as 1 over rho to some power at small rho. And so that's basically it. So we've blown through this chapter on Bessel functions. I would say then for the rest of the semester, we can do two things. And I think we should do two things. One thing we should do is, in class, discuss points that the students would like to rediscussed. In other words, what is it that you had the most trouble with? Or what is it that I explained most poorly? Put the blame on me. Secondly, there are more topics in the book that we could discuss. There's group theory, there's general relativity, there's probability and statistics. I'm not sure what you'd prefer to hear about it. My own preference would be to talk about general relativity because it's just intrinsically interesting, and contrary to rumors, it's not hard. It doesn't have to be hard. Any subject can be arbitrarily hard, okay? You can take the cylindrical Bessel functions of the second kind and bear down on them, and that can be arbitrarily hard. And you can do the same thing with general relativity. On the other hand, the basic understanding of both is relatively simple. And if you want, I can explain that to you. Also, gravity and cosmology are becoming more and more a part of physics now because of, well, the actual reason for that is the media. The media dominate everything. The media love pictures. Astronomers can produce pictures, and so they get tons of funding. They've got telescopes up the wazoo, and they discover things with their big telescopes. And so that's where most of the interest now is, because of the media. All right, after having angered the whole community of astronomers, I think we better end the... Is there a question before we...
When is the final again?
The final?
Yeah.
I don't know.
I think it's
But
Thursday.
it's... Huh?
Thursday?
Thursday?
Of which week?
2 weeks?
2 weeks from now?
The week of the 9th, right? That's the finals week.
Yeah.
Anyway, it's publicly available on the UNM web pages. I tell you what, I'll find out what it is and I'll announce it to class, and I'll put it on the class web page. All right, we can end this.